So let's go ahead and solve this problem. We have methane, and it burns with 90% theoretical air. So there's not enough oxygen. And the oxygen comes from air, so air also has nitrogen with it. Okay. And it forms an equilibrium, that's a key word given the chapter that we're in, equilibrium mixture of carbon dioxide, carbon monoxide, water, and hydrogen. So all those will behave as ideal gases in equilibrium mixture. They tell us also, nitrogen. They tell us the temperature and the pressure for that equilibrium mixture. Okay. Determine the composition of the equilibrium mixture. So what are you asked to solve for? The composition of the equilibrium mixture. Is that just one number? No, it's a set of numbers, isn't it? And what are those numbers? The mole fractions. You want to know the mole fractions of each of those components. Well, how many components are there? How many individual mole fractions are you asked to calculate? The mole fraction of carbon dioxide, the mole fraction of carbon monoxide, the water vapor, the hydrogen, and the nitrogen. So you're asked to calculate 5 things, the Y's, the 5, and if you add them up, that's 100%. Okay, how am we going to find that? Let me ask this. These are the products of the combustion. Is there any CH4? I mean, we didn't have enough oxygen to go around. It was deficient, 10% deficient. Is there any unburned methane in the products coming out? Not really. If you didn't study this chapter, if we only studied the previous chapter, we'd be forced to do something and say, oh, well, there's some unused methane coming out. But when you read this problem, if it says it's not in the equilibrium mixture, it's not in the equilibrium mixture. It's just not there. So there's no methane in the equilibrium mixture. That's kind of a big point. Let's do this. Is there any, I don't know, H2O2 in the equilibrium mixture? Nope. It's not listed. It's not there. Is there any NO in the equilibrium mixture? No, actually that's probably as viable a candidate to possibly have some of that going out in the real process, just like some unburned methane could go out in the real process. But this is a made-up problem, and they're basically saying these are the only components in the equilibrium mixture. There's no NO, there's no H2O2 or whatever, there's no CH4. It's only those things. Okay. So now we know what we're solving for and a little bit about the terminology of equilibrium mixture going out. How do we solve this problem? Well, I would do it in a few steps. I would get 100% theoretical air, write that equation down, and then leave it alone and write another equation for what's actually happening with deficient air, only 90% of the theoretical air that you need. So let's just do what we've done in the previous chapter. CH4 plus so much oxygen with 3.76 nitrogen. It goes to, if it was complete combustion, it would go to CO2s. I can balance the carbon right away. It would go to 1 carbon dioxide. It would go to so many waters. I'd balance the hydrogen right away. It'll be 2 there. I'd back balance the oxygen. And it's 1, 2, 3, 4. There's no oxygen with the fuel, so I need a 2 right there. And then if I want, I can just do the multiplication 2 times 3.76, and that gives us 7.52 nitrogen. I know that's not our real reaction, but that's the starting point to help us get toward the real reaction. True? So now, this is a little tricky. We're going to still think about a combustion, which is irreversible, but then we're going to have an equilibrium mixture of the products after the combustion. So what we'll do is we'll say, okay, I'm going to still come in with everything is going to be 1 kilomole of fuel, 1 quantity of the fuel. But we're going to not have 100%. We're only going to have 0.90 times 2 O2s plus 3.76 N2s. Do you see what we just did? Now, before I worry too much about that left-hand side, I'm just going to rewrite this right-hand side. Before I worry about the right-hand side, let me worry about the left hand. I'm going to write it this way. CH4 plus 1.8 O2s. Did I get that right? And then the 1.8 times the 3.76 gives me 6.768 N2s. Now I'm still going to use that single arrow and say none of that is in the products. What's really now the focus of the study is the products, and the products are going to have some carbon dioxide, some water. Let me do it this way. Because they put it in this list, carbon dioxide, carbon monoxide, let me keep that list. Carbon dioxide, some carbon monoxide, some water, some hydrogen, and some nitrogen. And now I know that I need to still balance these right here. And I need to put a coefficient right in front of this CO2. But this is all in a state of equilibrium. It's not in a state of equilibrium with methane that came in. There's no methane. It's like combustion happened, then I had products of combustion that are in equilibrium. Okay, but so one thing we can do right away is we can do an N balance. All right? How many nitrogen came in? Well, 6.768 N2s came in. Where is the only place? Is there any nitrogen here? Is there any nitrogen here? Any nitrogen here? The only place the nitrogen's at is right there. If we do a nitrogen balance, I can put down the final equilibrium coefficient in my mixture representing the number of moles that I'll have of nitrogen is 6.768. You say, that's pretty trivial. We're just going to keep doing that. We did a nitrogen balance. Great. Let's now do another balance. Let's do a carbon balance. It used to be where we say, well, there's one carbon here. And, well, I don't know how many moles in equilibrium of carbon dioxide I'll have. But for each mole of carbon dioxide, I'll have 1 mole of carbon with it. I also won't know how many moles of carbon monoxide I have in equilibrium of the products. But if there is, there's 1 carbon per each of those. So really what I'm having is it's kind of a mix. I have N, CO2 is the coefficient I'm looking for, N of CO, N of H2O, and N of H2. But those coefficients have to satisfy the equilibrium requirement, as well as the carbon balance and the oxygen balance and the hydrogen balance. Let's do the next balance, hydrogen balance. Excuse me. How many hydrogen coming in? 4. All right. None with the carbon dioxide, none with the carbon monoxide, but for every H2O, how many hydrogens do I have? 2. And for every H2, I'll have 2. Where are these equations coming from? Balancing the oxygen, balancing the hydrogen, and now the last one is the oxygen balance. What does that look like? Well, it's 1.8 times 2, because I'm going to balance O's. So that's 3.6 is equal to. And then I'm going to have, well, that many carbon dioxide. I'll have 2 O's for every one of those carbon dioxides. I'll have 1 oxygen with every carbon monoxide. I'll have 1 oxygen with every water, hydrogen, and that's it. I mean, there's nothing with the hydrogen only and nothing with the nitrogen. I'm going to pause. This is a bad looking H2O, but is that all understandable? Now, I can count my equations and count my unknowns. I've done this before. I have 4 unknowns. but only 3 equations. I need another equation. We get it from what's new in this chapter? The equilibrium constraint, which combines the conservation of energy and the second law of thermodynamics, and you have the Gibbs function, but it works out to a nice equation where you have an equilibrium constant K equal to. But I need to find a right equation, this sort of dissociation equation. Well, you'll go back into a table A27, and you say, basically, these are the only dissociation equations that we study in this introductory chapter, you know, but if you went to a chemistry text and really studied it, there would be a whole lot more. But how many columns do we have? 1, 2, 3, 4, 5, 6, 7, 8. You have to pick one of the 8. That's it. Just one of the 8 dissociations. And you look through them, and this one is the last one. And what does it have in it? It has that the carbon dioxide, CO2, plus the hydrogen dissociates back and forth between carbon monoxide and water. You say, yeah, it has all the players in it. It really doesn't matter. I mean, you may look at a different textbook and they may have it slightly different with a half or a 2, you know, multiply the whole equation by half or 2. But this one works just like this. This is our right equation. True? Does that make sense? Somebody says, I don't see any nitrogen in there. Well, what's the nitrogen doing? Nothing. And that is what we call behaves as if it was inert, inert. What does inert mean? Just doesn't participate. It's not breaking apart and combining with other things. Usually noble gases, let's say argon and helium, not helium. Is it helium? Yeah, helium. Argon, helium, neon. I'm forgetting. Xenon? Is it xenon? They like to be by themselves. They don't like to participate. Nothing. They just float around by themselves, right? Well, it's as if N2 is doing the same thing. We know that if you get it hot enough, it'll dissociate and it'll combine with any oxygen around there. But don't consider it for this made-up problem. So for that, what we're going to do is we look for our reaction equation K, or constant, and we have that's equal to 10 at 1600 Kelvin. We look across and we find it 10 to the plus 0.474 for that reaction. So that's what our K is, 10 to the plus 0.474. And then we remember the form. It's going to be the amount of the carbon monoxide, so let me write it like that, N of CO raised to the 1 power, the amount of water to the 1 power. I can't speak today. Professor, you haven't been able to speak clearly all semester. Oh well, I'm trying. Then you have the amount of carbon dioxide to the 1 and the amount of hydrogen to the 1. Then you had the actual pressure divided by the reference pressure, which is 1 atm. Then you had the total number of moles in the mixture. Let me write that out. That'll be the amount of CO2, the amount of CO, the amount of H2O, the amount of H2, and the amount of N2. And then it's raised to the power, the stoichiometric coefficient, 1 plus 1 minus 1 minus 1. Somebody looks at this and they say, how come you have the amount of N2 in there? Because it's the total number of moles in the mixture. Even it has to account for any inert gases that are in the ideal gas mixture, because it does affect the equilibrium composition. The presence of nitrogen will. Okay, or could, I should say. We understand the pressure right here, and we see that it's 1 atm. So we would put 1. What happens if it's 2 atm? Put 2 there. What happens if it's 5? Put the pressure of 5 atm there, okay? Somebody else says, look at this. In this whole bracket right here, I have 1 plus 1 minus 1 minus 1. I know what that is. 0. Now you recall from what's x to the 0. Is it either 0 or 1? You're good. You're real good. It's 1. So now that you know that anything to the 0th power is 1, does the pressure really affect the equilibrium mixture? Nope. It'll give you the same answer if it was 2 atm, 3 atm, or 5 atm. Also, does the presence of nitrogen for this problem affect it? No, it doesn't. It doesn't. The presence of nitrogen will not affect the equilibrium composition. Oh, it'll affect the mole fractions, but it's not like it's shifting it around. Because you'll have a percent of nitrogen in the mixture, that'll be a large Y, and it'll reduce all the other Y's. Okay, but this exponent up here is 0. So this really simplifies. This is all just 1. So now what we want to do is we have our fourth equation. We have 4 unknowns, but we want to do mathematically, just like what I've told you to anticipate on the final exam, a problem similar to this, where you'll have to set it up and then do a little algebraic manipulation. What we'll do is we'll introduce the variable Z. That'll be the number of moles of carbon monoxide in the final equilibrium mixture. Once we've picked that, then we can use this equation and say that anytime I see the number of moles of carbon dioxide, that's 1 minus Z, isn't it? And then we'll use this equation right here, running out of room, so we already know that's equal to 1. So this equation right here gives me the number of moles of H2O. Turns out to be, after a little algebra, 1.6 plus Z. And then back to this equation, the number of moles of hydrogen is 0.4 minus Z. Some algebraic steps there. Make sure that you can do it with confidence correctly. Once I have those, I substitute into this equation for K. So I'll have K is equal to 10 to the plus 0.474 equal to the number of moles of, that's Z to the 1 power. And then number of moles of H2O, that's going to be 1.6 plus Z. The number of moles of CO2, 1 minus Z. Number of moles of hydrogen, 0.4 minus Z. And you want to make that equation work. Now, this is one of those equations you could do it algebraically. You'll get a quadratic equation, and you can get, the quadratic formula. Do you have that memorized? X is plus, what is it? Minus B plus or minus the square root. Did I mess it up? Divided by 2a, so the quadratic, you can do it. But I even encourage you to do this on your calculator. Set it up and do it on your calculator, okay? Even though you could go further analytically, and you then would solve for Z. If you solve for Z, you find out that Z gives you the number of moles of carbon monoxide. It's 0.2236, which gives you the number of moles of carbon dioxide, 0.7764. And then you get the number of moles of hydrogen, H2, is 1.824. No, that's water, H2O, 1.824. And then the number of moles of H2, hydrogen, is 0.1764. And the number of moles of N2, don't forget the gas, inert gas, 6.768. I need to scoot down just a little bit so that when we sum them, we get the total number of moles of the gas 9.768. Then I can come back and I can calculate the percentages. It's 7.9% mole fraction. These are all the Y's. For the carbon, for the carbon monoxide, it's 2.3%. For the carbon dioxide, 7.9%. For the water, 17.7%. For the hydrogen, 1.8%. And a whopping 69.3% is the nitrogen. That's what we were asked to solve for. Another problem. Calculate the temperature at which 2% of diatomic hydrogen, which is H2, dissociates into monoatomic hydrogen at a pressure of 2 atm. This is a different problem, but it's using the same principles. What are we asked to solve for? The temperature. Often the temperature is given and you're asked to find equilibrium mixture. But here, really, they ask you to find the temperature and they give you information about the equilibrium mixture, which is that 2% of the diatomic hydrogen dissociates into monoatomic hydrogen. You take a look at your back of your table, you probably don't even need it for this one, and you find, oh, there's the dissociation of hydrogen equation, and it looks just like this. You have one H2, and it can dissociate into two H's. That's about as simple as they get. I mean, you can't hardly get any easier, true? And so you think about having the initial, and then you have some final. So think about conceptually, I have a tank, and I fill that tank with pure, nothing but pure hydrogen. True? And it'll all come in as H2. None of it will be disassociated. But then, after it reaches a pressure of 2 atm, and after it reaches a temperature which I need to calculate, 2% of that initial amount of hydrogen will have dissociated. So think about this. Start with 1 kilomole of H2. And play the game in your mind and say, let's do this. Let's let it dissociate such that I have left over 0.99 kilomoles of H2, right? Well then, how many kilomoles of H2 dissociated? 0.01. So in this case, 0.01 kilomoles of H2 DISS, dissociate. This does not dissociate, it remains. All right, so if that much dissociates, how much H do I have? Do I have 0.01 kilomole of hydrogen, or do I have 0.05, or do I have 0.02 kilomoles of hydrogen? The key is, how much dissociated? 0.01 kilomoles. So if 0.01 kilomoles of hydrogen, H2, diatomic hydrogen, dissociate, how many kilomoles of H do I get? Monoatomic hydrogen. And it's one of these three answers. 0.02. You get 0.02. This is a big step. You got to figure that one out. I mean, it's hard to do sometimes, but there you go. Now, this is what I have. This is what I have in the mixture. At the final state, at the equilibrium state. How many total? So it's like I have this amount of H2, this amount of H. How many total moles do I have in the tank? If I started with 1 kilomole, but I had 1% dissociate, how much do I have in the tank? Just add them up. 1.01 kilomoles total. True? Okay, well, you just worked that out for 1% dissociation. Do it now for 2%. How does it change your answers? How does it change these numbers? What will you have? You'll start with 1 kilomole. What will you have at the end?
1.03.
I'm sorry, right here. It'll just go slowly. 0.98. And then what will you have for the monoatomic hydrogen? 0.04 kilomole of monoatomic hydrogen. And then the total will be 0.02. True? So that's really what they told us. By giving us this information, they told us the final equilibrium composition. It's this much, and that much. Okay? All right, so let's do this. What's our equation? We had K as a function of temperature is equal to, just looking at this equation, the amount of hydrogen raised to the 2 power divided by the amount of diatomic hydrogen raised to the 1 power, pressure divided by 1 atm divided by the total N, which is, I'll just put it total N, raised to the power 2 minus 1. Where did we get the 2 and where did we get the 1? That's where we got them. So for this problem, I know conceptually I started with 1 kilomole of diatomic hydrogen, but it conservation works. So let's just substitute our numbers. What we'll have is 0.04 quantities squared. Did I do that right? Divided by 0.98. The pressure is 2 divided by 1 divided by 1.02. Did I do that math right? Do you agree? To the 1 power. Do you have a calculator? Somebody want to run that for me real fast? Zero point. What do I pick up on that one? What'd you get? Something like that. Now what do I do to get the temperature? Well, I have to find the temperature such that the actual K gives me that value of 0.0032. So you go to the table A22 and you say, I know that they give me in this table the log base 10 of K. So probably I know what K is. K is that value. What's the log base 10 of K? Can your calculator reproduce this number? Don't mess up coming into the final exam without refreshing your memory on how to do logs and etc. Can you see how it's negative 2.4927? And so I look down here for negative 2.49. You know what? Isn't that close enough? I know I could do a little interpolation, but guess what my temperature is? Isn't it 2700 Kelvin? That's my answer. So that's the temperature at which 2% of the hydrogen will have dissociated in that tank of pure hydrogen. So normally, you're given a temperature, you come down and get a K. This problem, you're given information so you can calculate the K, come down and get the temperature. Make sense? I'm going to press on then. Phase equilibrium. Think about I have a vapor and then I have a liquid. What is the criteria by which these are in equilibrium? Well, it's very interesting. I know we didn't spend a lot of time on this new thermodynamic function, lowercase g. Oh, what was lowercase g? Gibbs function. It was a lot like the exergy. It's H minus Ts. But it's very interesting. You calculate the Gibbs function for the vapor, you calculate the Gibbs function for the liquid, and guess what is equal to each other? The Gibbs function for the vapor is equal to the Gibbs function for the liquid. And you can even test this. All right? So right here is a problem. It says, use property data from the steam tables. What's in the steam tables? Enthalpies and entropies. And show that the specific Gibbs function, that's the lowercase g, so specific Gibbs function, which is defined as H minus Ts, of saturated liquid and saturated vapor are equal for steam at a given temperature of 150. So it's like this. You say, I'm going to try this. I'm going to calculate G, and this is where the subscripts and everything else gets a little tricky, because if we said H of F, what would you say? That's the enthalpy of saturated liquid. If we said H of G, what would you say? Oh, that's the enthalpy of saturated vapor. True. So why don't we say, hell, we have a new G, which is Gibbs function, and I want G at F and compare it with G at G. Now, that's very confusing because G sub G, that looks just crazy, but it's the saturated vapors specific Gibbs function. And G sub F, that sounds like a Gibbs function of formation, doesn't it? I'm sorry, but let's just do it this way. How would we calculate? We would say H of F minus T times S of F, and then we would compare that with H of G minus T times S of G. And so you get the values out of the steam table for 150. You have to put 150 plus 273.15 to convert that temperature to Kelvin. And when you do the math, you find out that the specific Gibbs function for saturated liquid is exactly or close enough to 4 or 5 significant digits for the saturated vapor. And I'm looking for my notes to see what value it is. It's 147 kilojoules per kilogram, good to 3 digits. So that Gibbs function, we don't spend a lot of time on it. Very little time on it. It was key for equilibrium conditions. It's key for equilibrium conditions of between phases. All right.